Welcome everyone to the BWorks Summer Institute UAS SAR course, or Unmanned Aerial Systems Synthetic Aperture Radar course. I am Ben Marcotte of Lincoln Labs, and I am the lead instructor this year. Synthetic Aperture Radar, or SAR, is a radar imaging technique that is used to image the surface of the world. SAR is typically applied by not only our nation's military, but also by planetary and climate scientists. During this course, the students work in teams to develop and operate a fully functioning SAR imaging platform. They do this by assembling multiple hardware systems, along with writing all of the software-based commands, communication, and processing to develop images. Through an iterative fly-fix-fly development process, the students incrementally improve their complex systems to make them more efficient, more practical, and more user-friendly. The concepts in this class are typically reserved for graduate-level students or even working professionals. So in order to be successful, the students need to show advanced technical abilities, superior teamwork, and a drive to perfection beyond what their normal coursework requires. This course is a chance for students to solve real-world engineering problems, and it provides them with an insight into the STEM world that most people do not get until they are already in the workforce. It is also a chance for the students to prove that they are up for a challenge. Thank you for your time, and again, welcome to UAS SAR. So before we go ahead and get started, I'm going to kind of explain what we're going to be doing here a little bit more than what we did inside. So the idea here is that the radar system can see through objects that will optically distort other systems. So right now, nobody can see through that piece of paper, right? And we're going to prove to you that their radar systems, using back projection, can tell where people are going to be within this grid system just by using radar collections. So we're going to want volunteers for this who are going to act as the radar scatterers. All right, so we already got some, I see 3 right here. We'll take these 3 forward first. And I promise this is completely safe because as you saw in there, we are being drowned out by 5 gigahertz Wi-Fi routers, so our signal is way weaker than that. So what we're gonna do is at some point we're gonna get you whiteboards and we're gonna want you to write your coordinates down on those whiteboards. So know where you are, and we're going to make sure that they're actually getting your proper position.
Overview of what this is. These are the 3 people that were standing in the sea. And then along both sides we have the distance in meters, measuring where they were.
And this is the paper that we scanned behind. So I'll talk about it. Any questions?
So the way this runs is we have combinations of 3 different models. So this is basically just to denoise it, and if you look in the top left, that's kind of the original image we get. And with a different combination of like filters we do, it should give different types of results. So that's what's on the other screen. And after choosing one of the appropriate models so we chose the median image because we thought that was the best, but there's a bunch of different combinations to try and different settings within that, which is here. And we determined that we thought this was the best one, and we also have it reoriented so that it matches what you actually would see from the radar's perspective. So yeah, that's our SAR image.
Yeah, and this is at a centimeter resolution, so we could have ran this at a higher resolution if we wanted, but yeah.
Any questions? Okay, cool.
All right.
What do we have for coordinates of the... Yes. So Michael has the truth data.
Okay, hold on. I'm going to need some expert opinions and double check it.
Or 5.75.
Yeah. What's this? 1.5 and like
5.75.
5. This, yeah, basically it's 6.
6
Or,
Oh, feet? Oh, yeah, that's... Feet to meters.
Wait, not by... Okay. All right, so let's divide those by 3. So you got 6 on the x-axis, so we got about 3 meters by...
Wait, we're in meters.
You're in meters. Or sorry, 3 feet. No, sorry, 18 feet. And what is that?
about 1.5
feet. We don't have any metric ones.
So about 4 or 5 feet.
Okay, so do we have anybody at 4 on the x-axis and 18 on the y-axis?
We've got 8, 22.
All right, 8 and 22.
No, that's in feet. 822 is feet.
But did you convert that, or what is that?
That's in feet. So that's the raw.
All right. Okay. Let's go ahead and get, is team 4 ready for a data collect? right, we'll get Team 4 ready for data collect, and we'll come back to this this positional reporting. All right, Team 4, give us a thumbs up when you're ready. All right, radar targets, are we ready? Thumbs up, we good? All right, Team 4, go ahead.
So what do I first talk about?
Unsure if this will work.
Second mic, so they don't have to.
Okay, thank you.
That worked.
Good? All right, let us know when you have back projection.
We have it.
All right, Team 2. Yeah, so regular targets, you can come back. Just keep your positions written down on there, and we're going to note them down.
All right, so here's our beautiful back projection with blob detection. Oh, did it?
Like,
Oh.
What's happening?
Cable came to this? Is it up?
Push this in.
I'll just lay it down. Nothing?
You can't see it on the screen.
Oh, it's coming up.
It's coming up. Okay.
Just my desktop. Uh-oh. I'm just... disconnect and reconnect. Just keep talking.
So if you can see from this laptop here, there's two really concentrated points. So like this big area in red, and then this one in yellow. The radar focused more on the red area, and it kind of washed out this one. But there are two individuals here, and using our blob detection algorithm in the terminal. It's kind of hard to see, but we printed out all potential blobs, and these bottom two are the exact coordinates in meters of our two blobs, and we did this using our GUI system. Over here, where we were able to easily start scanning. So while I was walking, we started scanning, and then once I got to the end, we stopped scanning. And then through this GUI system, we're also really easily able to generate, is this heat map?
Yeah, this is heat map.
Heat map to just determine if we actually saw some targets. So these thicker lines, more concentrated lines are potential targets.
Alright. Yeah. Everything?
And
yes, so we have our locations
oh yeah.
written down back here.
All right. Do we need to convert to inches?
Nope, we are in meters now.
All right. So one individual was at, for the x-axis, 1.52 meters. For the y-axis, 6.41 meters. And then the other individual was, for the x-axis, 7.13 meters. And then for the y-axis, 7.87 meters, give or take.
All right, read that first one off again.
Is that one? Are you sure that's accurate?
Yeah, looks reasonably right.
All right, go back. 1.52 on the x-axis, 6.41 on the y-axis.
All right, so we got a 3.3 and an 8.3. So that is pretty good with a not tracked at all motion capture system. So, all right, what's the next one?
Oh, the next blob?
Yep, next
All
block.
right. 7.12 or 13 on the x-axis, 7.87
All
on
right,
the
so we got a
y-axis.
6.4 and an 8.6. So that is pretty good. We got both targets in there. Congratulations.
Thank you.
All right, thank you very much. Do we have Team 5 ready for a data collection? All right, well, we're waiting on Team 5. Can we get radar target volunteers for the Team 5 data collection? Anybody want to come up here? Be a part of the demo? All right, come on up. Come on up. Yeah, you can absolutely do that. See how it affects the data. So we'll do that not for this one, but we'll do it for the next remote setup. Yes. All right. Do we want any other volunteers? All right, we're going with 2. Feel free to come on up. You want to do it? You can both go in together if you want. You can both go in together if you want. Okay. Yeah. Absolutely. So yeah, once we're done with this testing, we can bring it up now. Okay. Tell them to come back up, and then they're going to do another data collect after that too. Team 1? Yeah. Yes. So they can show their data and then run it. Yep. Yes. So looks like our radar targets are ready. Team 5 is ready. You can go ahead whenever you want. So the next collection that we're going to do another collection.
Oh, okay.
So you can show off your data first and then do another collection. And this time, if you want, you can plug into Okay, you want to share your data?
Yeah, so that's the main thing. We can just hold it up.
We can show.
So yeah, if you want to plug in.
Okay. Is that right?
Yes. So if you're ready to come back up. All right, Team 5, we all set? All right, let us know when you have a back projected image. Radar targets, we're all set. So bring your whiteboards up here and we'll mark down your positions. Team 4, are you ready to show your live back projection? Okay. And we're waiting on Team 1 to come back up with their data. Yeah, absolutely. All right, we're going to have a redo. Team 5 is going to come back out. So we need more radar volunteers, radar target volunteers. Anybody? All right, come on up. All right, Team 5 is starting their data collection. Okay. So Team 1. Do you have the first? You can just hang out here for now. So what we're also doing is for a second time. This time you're going to put you're running. You're going to plug it.
Is it just divided by 3?
All right, Team 5, we're all set. Okay. All right, so. All right, so we're going to go back to Team 1. What was your original positions that you had for the targets? Do you have that up? All right, so you want to read them off?
We don't.
So we have it. Oh, yours is in feet now? Okay.
Yeah, we converted it.
All right, go ahead and read off one of the positions.
Just say that.
5 feet. X is 5 feet and the Y is 12.
Looks like we got a 2. Oh yeah, 4 and 13. Yeah, there you go.
Okay. We have X at 12.5 and Y at 23.5.
So 13 and 33. What was that?
23.5.
And 12.
12.
Might be the one on the bottom. You didn't have an X. They didn't write down the X-axis. Oh, sorry. Yeah, one of our targets didn't write down their multiple coordinates. So what's the third one?
22.9 x, and then y is 10.4.
I think we got messed up here, so that's on us.
Okay.
So we're gonna give Team One another chance to go ahead here.
Okay.
And this time we're gonna get to watch their collection process as well. So somebody from their team can go ahead and plug into the screen. So for those of you who missed the indoor presentation for this, this was all put together in about a day and a half by these students. So they are pulling off some absolute miracles up here. So part of the fun with being out here is that we don't have 5 gigahertz Wi-Fi, which is why our radars actually work out here. So part of the problem, but also part of the solution. So.
See it there? Open your giving. Yeah. So this is what our GUI looks like. We have an updated version, but we haven't had a chance to test it yet. So I didn't want to change too many variables before we tested today. So we're just using the old one. We do have a better one. So basically, whenever we want to start scan, we just press that. It communicates with the Raspberry Pi. And if we press end, it'll stop it. We have to wait about 5 seconds for the code to write a file. And then we can press download. And once we press download, it should automatically make a range time intensity plot of the data that we just got. And then the update code just pushes updates to any code that we've made automatically without having to do any like command line commands or anything that can get annoying. Are we ready to run?
Yeah, we're ready to run. I need you to yell countdown. Yeah. Okay. So we're gonna count down. He's gonna start the radar from here, and then she's gonna start walking. So countdown. All right. You guys ready? You guys ready? Oh yeah, we need targets first.
Yes, we do need targets. So who wants to volunteer? Come on up. Sample space as tightly as possible, or else you're going to have something called aliasing, which is that you aren't able to actually resolve the targets apart from each other, and there could be multiple locations that could exist. So the slower they move, the better their radar will. All right, looks like our targets are ready. Team 1, are we ready to go?
Yeah. All right. 3, 2, 1, start. Yeah. All right, get ready. Not yet. And stop. Okay, now send me that file. Yep. We gotta wait a second. Bring the radar over here. Yeah, bring the radar over here.
All right, thank you very much.
Is it popped up? Okay, so there's our automatic range time intensity plot. Watch out real quick. So whenever we process the data, we do slice this out. This is leakage from the radar. So basically, because those two antennae are so close to each other, some of the transmitting signal goes to the receiving antenna, and it causes all that leakage, which is kind of annoying, but it is what it is. We just slice that out whenever we process the data. But that's what our range time intensity plot looks like. We're going to switch over to...
All right, so now we're watching their back projection process.
Well, first we're actually getting the... No, you should explain because you're doing
Yeah.
it. But...
So now we're gonna take the radar file and we're gonna create the motion capture for it. So
So if you were at the presentation, we would normally have the actual motion capture data from the high bay, from the cameras, but because we don't right now, what you can see Ojus is doing is he's basically emulating the high bays. So like the motion capture data from the high bay, and then after that, we're going to back project, and that should be it after we do our denoising.
Also, we have different files on different computers right now, which isn't the best way to do this. But we haven't had time to test if it all works on one laptop, and so we don't want to change too many things before the final event and have a lot of things go wrong. So we're sticking with our kind of inefficient workflow for now.
It looks very efficient to me.
So right now you can see on the file that this is the motion capture we are creating. So we take the time that it took for the scan that we get from the radar data, as well as the total distance that we input ourselves. And using that, we create our data points here. And as you can see, the X values changing as Rhea walked towards us, which is the X values. The Y value is based on her height and how she's holding the radar, where she's holding the radar. And the Z is a consistent 0 value since we're going in a straight line. All right. Let me send you the file.
Airdrop, don't Discord, because we have less
There's a problem with the UI. Just to narrate what's going on right now, so in order to back project the image, you need both the radar data and the motion capture data. So that's the file transfer that's going on right now in order to get our final back projected image. Do you want to say your question?
Yeah, I just ask where's the sensor for the motion capture,
So in our original final event, we had an actual motion capture system in the high bay with very accurate coordinates. Since the high bay was no longer a viable option, we are simulating motion capture data using a grid system.
So pretty much that's how we're getting. So per scan, we need an XYZ coordinate plane. And so if we don't have the high motion capture to give us that exact coordinate point, we are taking the total distance that we travel. So right now it's about 30 feet. And then we're taking the total time, which is about 28 seconds we took. And that's how we got our average velocity. And using that, we are plugging in the times per. So like whatever scan we get, we figure out the timestamp for it. And using that time, we put it into a function for the average velocity. So we can figure out exactly where we want our XYZ coordinate. And using that, we add that velocity number to each X coordinate. So that's how we're pretty much simulating our XYZ coordinates to get our motion capture. Yeah, that's why we...
Okay, so what I did right now is that I converted the both of the motion capture file and the radar data file because I first wrote my back projection algorithm for the marathon files. I have a convert.py file that takes those two datas and then converts it into the correct format for back projection, which I'm about to run now. So I'm going to run this at a centimeter resolution over 10 meters by 10 meters starting at 0,0. And the process is like quite computationally intensive, so we have to wait a couple seconds for this to run. And once it does, a graph should pop up with the back projected image, which we are next gonna send to Charlie's computer to denoise. So yeah, we have back projection.
Woo! All right, so we're gonna have another data collection from Team 5. So can we get more volunteers to come on up here and be a part of the demo? There you go. All right, we want one more. Anybody else want to come up? Yeah. All right. You can go. Yeah, thanks. Yeah, that works. So you're going to pick an X and Y coordinate on here. So X being in this direction and Y being in this direction. So write down the exact number of feet that you are within both of those. So walk along the X and pick it out. All right, looks like our radar targets are ready. Oh, you're already collecting. I probably messed that up a little bit, but it'll be okay. Yeah. All right, thank you, radar targets. Thank you, Team 5.
All right. So what you just saw was we sent over the back projected file from a purpose computer. Oh, It's already done. Okay. And this is after denoising. So I have, like you saw earlier, there are 3 different pictures that you get. So looking through them, we're going to first take a look at the different combinations of filtering algorithms and denoising algorithms to see which one gives us the best return. So last time we had it on median image, and to be honest, this time it doesn't look great. So I think we're going to change to a different filtering model. So yeah, looking at this, I'm thinking we should use Gaussian image. So if I go into the code, I can just really quickly change that.
Yeah, I'll talk back once. Yeah, sure. If it breaks, I'll pay you.
I'm thinking we should change the kernel value as well to 6. And so yeah, there I just changed the model to the Gaussian filter by itself, and also I changed the sigma value. So this is the image that we're getting now. So as you can see, you can make out very clearly that we have one like point of interest here that has a really high intensity value, but you can also make out there are 2 others here. So a big potential issue, or a potential reason rather, why we have a much higher return from this is potentially like non-constant velocity. And that was kind of one of the bigger problems with doing this outside, where walking, it's kind of hard to maintain a perfectly constant velocity. So if that was the case, we could have had more scans towards the end over here with this object versus the other 2, which could have been one of the causes for why we see this so much clearer than the others. But from this, you can definitely make out that there are 3 distinct objects in the scene.
Which team is it?
Team 1.
We're team 1, yeah.
All right. So what do you have for positions for the 3 targets?
We have everything here in meters, by the way.
Okay. I have it in both. So.
Oh, he has them both. He has.
Yep, I have it in meters.
All right, so.
No, let's just give it how it is here. So that's like 7.
Okay.
So one of them is at X is 7 meters. 7 meters.
No, he has.
Yep, meters.
So 6.5, 7 meters. And a Y of about 3.5 meters.
All right, we got a 6.7 and a 4.5.
Okay. A second one at X is 2 meters, and that looks like 5.5, 6.
6, yeah, pretty
Yeah.
much 6.
So we got a 1.5 and a 6.4.
All right.
Okay.
Okay. And then.
And final one at about 7 3/4, 7.75, and about 6.5.
Yeah.
So we had a 7.6 and a 6.7. So that is exactly dead on for that one.
All right.
Great job.
Did we win?
Okay.
We won.
We won. Yeah. You can go get one.
All right. Thank you.
I think that was because we hadn't set it 0, the start range.
All right. So we're gonna take a quick break while we're waiting for teams to get lunch and waiting for a couple other teams to back project. Yeah. All right. So folks, we have Team 3 ready to present their results from their collection.
Okay, so this first one that we have up here is a range time plot. So going to the right, the farther away the objects are, and going down, you can see as time progresses. But you can see at the top and the bottom.
Or from the speaker, just a little
Okay,
bit.
and you can see at the top and the bottom, there's these areas where the values are a little bit sort of stationary. So what we first do is we just chop those off to get this more cleaned up version. And then we ran our first back projection. It's a little bit on the messier side. But then when we zoomed in, it started to become clearer, and you can kind of see. Do you want to do the rest?
Yeah, so over here, we zoomed into the high intensity points, and we have 2 really bright objects towards the bottom, and then like a sort of blob towards the top. We're not sure how many objects are there, so we did more filtering. and then we got 2 really bright spots and 1 faint one up there. And the locations we got were we got it's in meters, so we got 7.5 and 7.5.
Yep.
And then
So
we
7.3 and a 6.3. So that's good.
Then we had 1.5, 7.5.
So what? 2.6 and 6.3. So that's good too.
And then we had 1.5, 11.5.
And that one, I think we got something wrong there. But you got 2 out of 3, so that's pretty good. Congratulations, nice job. All right, so soon we're gonna have Team 2 come up and do what Team 1 just did, where they're gonna walk us through their workflow, and we're gonna do live back projection, somewhat live. So do we have any volunteers to be radar targets out here? Anybody new? Anybody that hasn't done it that's interested? I'll definitely take repeat customers too. So yeah, if you wanna, we're gonna do like show the whole process of the selection. Alright, there you go.
Ben, where's the HDMI cable?
I think you can go ahead and do that.
Oh.
Okay. There you go. All right.
Hopefully this works. Does that work? Well, no.
Give it a sec. It takes a minute sometimes.
HDMI, please okay less. How is it that both are computer? Oh, there we go. There we go. Okay, so yeah, this is a UI that we hooked up. Oh, great. Oh, that's loud. So my buddy over there, Rashid, has the radar ready. So we have something called dynamic scanning, so we can start and stop our scans willy-nilly. So all I have to do is hit this start scan button. Rashid, are you ready? All right, starting scan. So as you see, as our scans are coming in, I'll record how many are coming in. And after this is done, a few seconds later, we can pull up range time plots. And we have, I believe, the fastest SAR processing, so we can also do SAR in a couple seconds. Ending scan. Oh, God. There we go. So this is range time plot, if I can pull it up. Come on. So this is the range time plot of our scan we just did.
Yeah, so we're gonna see what that looks like.
And let's quickly
So
put.
we actually had some radar targets moving during that collect, so you're gonna get to see what the problem is with the moving target in a back projected image.
So let's see.
Yep.
Like.
We had some full steps, so.
Okay. So let's see. Can we identify the full steps? It might be this.
Yeah.
So these are supposed to be like continuous curves, but we can see he was moving. We can see him right here.
That's all right.
Through the wall.
This is a cool thing. We get to actually show what that looks like.
All right, so let's try to get back projection working. All right. All right, take 2. Let's go. Starting. It is working. We're scanning right now. Your laptop has the wrong code on it. Yeah. Faster, just switch. Call it when you're done. Oh shoot! You guys looked at my screenshots? No. Yeah, you look at your screenshots. Good. That's a lot of stuff. So as we see on here, none of our targets moved this time, since all our lines are nice and smooth. And if we chuck this into back projection,
Yes.
are you sure your code won't crush this time?
I hope so.
So we picked up a couple targets. So we see 3 targets, and our blob detection did pick everyone up. So yeah. Coordinates, let's go check our code.
Should be 6 or 8. All right, well, good enough.
So let's see.
Okay, go back to the heat map so we can compare. Okay, so we have one at about 3.7. Okay, check. Go back. All right, so.
Positive coordinates. So these.
All right. So we have one at 3.59 for the x-axis,
Okay.
and then 6.21 for the y-axis.
Sorry, I can't do math that fast. Okay, sorry, say that one again.
3.59,
Okay.
and then 6.21.
All right, so we had a 3.3 and a 9.
And
That's pretty
9.
close.
5.52.
Okay. And then we have a 5.52,
5.3 and
5.52.
6.
All right.
All right.
Okay.
And then
Last one.
one more.
Last one is all the way off.
Yeah. 14.98,
7.57.
and then 7.57.
He might have been on the edge somewhere, so we didn't get enough energy on him.
Okay, I honestly don't know which one of these 3 boards is the last person, so you're probably right.
Okay. Cool.
All right.
All right, nice job. Team 4, are you ready to collect again? Okay.
Talk about the screenshots. You saw them? Kidding. Okay, good. More concerning is your password. Why?
All right, Team 5, you have a back projected image you want to show, right? All right, you want to bring it over?
I do.
All right. Joel, there you go. Marker. So you erase that, and then you go pick your coordinate over there. So x-axis this way, y-axis is out.
Yeah.
Yep. I don't think that one works actually, so you take that one.
Yeah.
There we go, and then where's our third marker?
Third marker might have rolled off. If you look at the ground, how long have you been?
It's there.
All right, there.
It's there.
All right, yeah. How long have you guys been having lunch for?
What?
How long have you? When did you guys
I'm
start?
not eating lunch.
Hold off on the data collect for a sec.
Did they like take a break?
I took a group to get lunch.
Oh, okay. You didn't bring any.
I didn't have any time. I can't eat here anyways.
You didn't bring any lunch?
I did.
All right, Team 4, you got your setup here?
So we're just gonna run our client data collection. So you'll see 3 graphs. One which is the current frame of where it is in position. One is our back projected image. And the other is the raw scan data that we're pulling in, right? The raw analog signal. So whenever the targets are ready. All right. 3, 2, 1, go. So this is our live back projected image here, this first graph. This next one is the frame of where it is in position, and then this last one is our signal data that we're receiving. So if you take a look at all of these. Yeah, it's just raw signal. And this is okay. So we can try back projecting heat here. So, but yeah, I already did. I did that while I was gone. We can run back projection.
Are they good?
Oh yeah.
All right, radar targets, we're all set. Thank you very much.
The graph
Wasn't?
was good. Like you could see 3, and they were all.
So this is our back projection. Yeah, it's right here. Yeah. Okay. So we have 3 targets in our image. We have one right here. We have another in the corner, and another over here. So reading it out in meters. Do you guys have it in meters?
Yep, we got it. Meters.
Okay. So one target at 5.97, 4.90.
All right, we got a 4.5 and a 5.1.
Another at 2.05 and 8.23.
1.66 and 9.67.
And then our final one at 8.47, 9.74.
10 and 11. So there you go. Nice job. All right, Team 5, you ready to show what you got? Yeah. Team 3, are you going to want to collect after this? All right, get up here. So she has a mic.
Oh, Midge? Yeah. So, here are 3 targets in the scene. Yeah. our coordinate axes are incorrect because the radar has a slight range offset and it doesn't fully calculate the ranges correctly. But the distances between them should be proportionally correct. And we also have denoising here so that we can see the targets more clearly.
Yeah, so as previously stated, the axes are not necessarily correct, but you can see that the way they are proportionally to each other matches the way that the coordinates are. So I have them plotted out here, and you can see that it makes roughly around the same shape with the dots on the plot as the SAR image here.
Yeah, also, Ben was, I think, moving while we were doing the data collection, so that might be why there's like slight strange smudging here, and the third target isn't very easily made out. But
Is that the one on the right side of the image? Yep, that's absolutely me. You're welcome.
Okay. Thank you, Ben.
All right, thank you very much. Great job, Team 5. All right, Team 3, you ready to collect? And this will be our last one for today. All right, 2 more targets. Anybody want to volunteer?
Volunteers? 2 more?
You can get creative with your formations.
All right, Max. Yeah, come on.
Yeah, maybe make it bigger because we couldn't really see.
Okay, so right now, Ishan is increasing the range. By play. We are now running. Yeah. Okay, we're running the client. Soon. Soon. Now we're running the client.
Ours is super consistent because Johan is listening to a metronome. 60 BPM. Nice slow tempo.
1 foot at a time. All right.
All right, thank you, radar targets.
Okay, we're downloading the file.
The board is definitely...
Now we're opening the range time plot. And it went blank. Oh, it's back. Yeah, 2 and 32. Maybe don't cut off. Oh, 32, I guess. So we're cutting off the times where we weren't moving, which is at 2 seconds and after 32 seconds. Yeah?
Yeah, right? You're just consistently losing that.
Stop receiving for a certain time every and like at some seconds. So we have 3 things.
Yeah, like
I'm gonna
1,
zoom
2,
into
3.
that.
7, -9 origin.
So now we're zooming in. Oh, it's loading. We're processing so much data, and we're not using C++, so it's kind of slow. Are we? No, we are not using Python.
We have a high resolution right now, which is why it's taking some time. Oh, but you can see it. Like 3 objects. You can see it like 8.5, 7.5, 2.5, 7.5.
All right, so we got a 6.9 and 9.3.
Yeah, 7.5, yeah.
And then we have 2.5, 8, and then 7, 11.
You want to read those off one more time?
So we have 2.5, 7.5, or a little bit more than 7.5.
So then we got a 4.5 and a 5.1, so that's right.
We have 7.5, 7.5.
7 and a 9.3, so that's right.
And 7 and like 11.5.
All right, we got an 8 and a 10. So there you go. Great job. All right, so that is all we have for today. Thank you all for coming. Great job, all the teams. That was successful back projection, successful SAR from everybody, doing it on a completely new demo that no one has ever done before, done in a day. So congratulations, that was amazing. So the next step is we're going to head over to the ice rink in a bit, and then we're going to have the closing ceremony over there. So we're going to pack up here, and then we'll meet you all over there.